A beer afterwards, because all my buddies have just gone across to the Brunswick, so I'll be going for one afterwards. But hopefully we'll see you all in person at some point in the future, nevertheless. Anyhow, tonight's chat all about the Class 93 programme, our new Stadler tri-mode locomotives. So what I wanted to do really is cover 5 different areas. Number one, how did it all start? You know, what commenced, what sparked off this Class 93 concept? Second bit, I want to have a little talk through the technical specification of the locomotive. You know, it's a very rounded locomotive. I want to go into a little bit of detail as to what makes it tick. We'll have a little chat about the build program as the third part of the talk, and how things are progressing with the build program. Fourthly, I want to have a little talk about what happens with the 93s when they enter traffic, you know, so the 93s capability and indeed their performance ability as well. And finally, you know, some of the markets that we'll be pointing the Class 93 at. So it's a full holistic presentation from start right through to the future. And as Martin already said, you know, there are about 3 places within the presentation where we change tack, and that is really an appropriate point for me to answer any questions, whilst the questions still have some meaning, some relevance, and some context, rather than waiting right till the end and then asking questions about something that happened right at the beginning of the presentation, which sometimes doesn't work. So plenty of opportunity to ask questions. Please type them in, as Martin said. Get typing away any questions you like, and if I can answer them, I will. If I can't, I shall try and find out the answer. I'd like to think I do know all the answers. After all, it's my locomotive, so if I don't know the answer to something seriously wrong, but there we go. Right, let's get cracking. So like I said, where did it all start? So I guess it was back in 2018 when, you know, as part of the business planning process, we recognised as a growing company, a growing train operating company, that we needed some new locomotives. We were operating a fleet of 37s, 47s, 57s. They're all old girls, whether they've been re-engineered, modified, or what. You know, they're still basically 60-year-old locomotives. And, you know, whilst they do a job to a certain extent, they're certainly not a locomotive of the future. There's lots of things that they're incapable of doing. You know, the landscapes are changing out there, especially in terms of things like environmental impact. And you know, whilst you can.
But Carl, sorry for interrupting. We can't see the presentation.
No, there isn't one yet.
Fine. Okay. Fine.
I shall tip you off when I'm going to launch into
Sorry about that.
The slide. So it's just a bit of a chin wag to begin with. So yeah, you know, there's lots of things you can't do with those locomotives. You know, you can re-engineer them, but at the end of the day, they're still an old locomotive. And we decided, no, if we're going to go for new locomotives, they have to be brand spanking new locomotives designed for the next 60 years, not the last 60 years. So, you know, we also recognised as well that the specialist operations we do in Rail Operations Group, most of you probably know that we are a specialist operator. We deal a lot with the rolling stock engineering community, you know, hauling EMUs around for various reasons, testing EMUs, living DMUs, and doing all kinds of midlife stuff as well, hauling EMUs around. We knew that market was going to level off, and indeed probably begin to diminish as more and more new train fleets were, if you like, a part of a build and maintain program. So, you know, gone are the days when we're going to be hauling fleets of EMUs from one location to a works to undertake modifications. That's not going to happen in the future. It's all going to be done at the home depot. So that's what drove a diversification program. So we said, well, hang on a minute, we're a train operating company. We've got a non-passenger license and a passenger license. We need to, diversify and do some other things as well. So we started looking at high-speed logistics. We started looking at freight. And obviously what we needed was a locomotive to serve a multitude of different markets. And, we went to Stadler and, we said, we need some new locomotives, and we want them fairly soon. So we need to have a little chat around what you guys at Stadler can provide. So, we chatted around the 68. No, doesn't cut it. It wasn't a locomotive for us. It's a diesel locomotive. We wanted something a little bit more funky and powerful than a Class 68. The Class 88 was a better option for us, but unfortunately, it is pretty much still an electric locomotive with last mile capability. We wanted more a true bi-mode locomotive, so a locomotive that could, for example, part of the specification was there must be able to haul the 250-ton express passenger train off the wires at 100 miles an hour. And the Class 88 clearly couldn't do that. We even had a chat around the Eurodual, the big European bi-mode locomotive, which is now designated the Class 99. The Beacon Rail, they're developing the concept. But of course, the Eurodual doesn't fit onto the UK rail network. Whilst it might be the same track gauge, it's a much bigger locomotive in terms of its loading gauge, and it just doesn't fit the UK rail network in exactly the same way. No other European vehicle fits the UK rail network. We're still stuck with a Victorian gauge profile, unfortunately. And you think to yourself, well, okay, we'll just shrink it. Well, it's not quite as easy as that. Stadler said to us, it would mean a complete redesign of the Eurodual locomotive, and a complete redesign takes a long time. You're basically designing a new locomotive, and so the redesign would mean our wait for the locomotive was going to be too long. Potentially 5 years from signing a deal to actually getting a UK sized Eurodual. It was going to be damned expensive because you're building a new locomotive essentially. And unfortunately, because it's a COCO, it's a 6-axle locomotive, you've got the problems arising from the rigidity of the bogie as well, which means track forces are higher, and it was suggested that we could expect a locomotive that could run no faster than 75 miles an hour. So the Eurodual didn't fit. But the 93 did. The 93 did, and that's what I'm going to share with you now. Let's put the first slide on. Let me just bear with me whilst share my screen. And I'm also going to make sure you can hear the sound. Right, so you should all be able to see that screen now. Martin?
That's fine. Yeah, we can see that. Thanks, Carl. Yeah.
Yeah. So like I say, we came up with this Class 93 concept, and the Class 93 was as close as we were ever going to get to the locomotive which fitted our bill. The one thing that I reckon we must all understand is it's impossible to get everything from a locomotive. A one-size-fits-all policy just doesn't work for locomotives. You can't have a locomotive that does everything. And this is why historically we've had dozens, if not hundreds, of different types of locomotives in the UK. They're all designed to do different things. And even with state-of-the-art technology, there's certain things that you can't expect to deliver in terms of fulfilling all the requirements of a locomotive. But what we did have with the Class 93 is a true mixed traffic locomotive. And I have to say, the specification is great. We're going to go through the spec in a minute. But I also have to say that the timing was right. You know, I am so glad, you know, we are not in the throes of ordering a new locomotive now, because, you know, since we ordered the Class 93s, the global supply chain has fallen apart. Raw material prices have gone through the roof and continue to go through the roof. And the Russian invasion of Ukraine is devastating steel production and manufacturing across Europe. And that is already beginning to impact on the UK rail market as it happens. So, yeah, timing is perfect with that. So let's have a little chat about what we can expect to see from the 93 when it arrives. Like I say, it's a very versatile locomotive. And what I want to talk about now is just some of the generic operating characteristics of the locomotive. First of all, it's a 4.6 megawatt locomotive when it's got the paddock on the 25 kV overhead. So 4.6 megawatts in old money translates into 6,250 horsepower. So, you know, one of the things to remember about an electric locomotive, when you talk about electric locomotive having 6,250 horsepower, that is 6,250 horsepower at the rail. You know, these locomotives have a 1.15 megawatt rating traction motor. So that's the power we can expect at the rail. With a diesel locomotive, when we talk about a diesel locomotive having 3,000 horsepower, for example, that's the power unit horsepower, not what you get at the rail. You know, I think, you know, most of you will understand that the power supplied by the power unit itself, some of that power is taken off to supply lots of other you know, auxiliary equipment and battery charging and cooling systems and God knows what else. And you know, there's a lot of energy lost in energy conversion. So typically you will lose anywhere between about 10–15% of your power output to auxiliary equipment, etc. And so, you know, that's why the power delivered to the rail with a diesel locomotive is somewhat less than its power unit output. What it's also got on board is a 900 kilowatt diesel alternator, which translates into about 1,350 horsepower. I think it is in old money, or thereabouts. It's a similar engine to what's in the Class 88. As we know, the Class 88 is an electric locomotive, and it's got a diesel alternator set on board. That's a 700 kilowatt engine. So this is an uprated version of bigger diesel alternator set than in the Class 88. But one of the big differences with the Class 93 is we're fitting lithium titanate oxide traction batteries. Now, what these batteries do is obviously provide power to the traction motors, but there's a reason why Stadler chose lithium titanate as opposed to lithium ion. You know, most battery vehicles, as we know, even locomotives with lithium batteries have opted for lithium ion. But the reason Stadler suggested lithium titanate is because the characteristic of titanate means that I can recharge the battery quicker than I can with a lithium oxide, a lithium ion battery. Now, of course, being able to recharge the battery quicker is much more appropriate for a locomotive. You know, when tractive effort demand is up and down like a yo-yo as the driver's opening the power controller, you know, easing back the power controller, you know, opening it up again, you know, to increase speed, closing it again for a speed restriction. So, you know, your tractive effort demand on a locomotive is up and down like a yo-yo. And a lithium titanate oxide battery, the characteristic aligns perfectly with that kind of mode of operation. So obviously when the driver eases the power controller back, I can recharge these batteries ready for when the driver reopens the power controller again. So it's got 3 different sources of energy, but interestingly, I can actually operate the locomotive in 4 different modes. So yep, I can operate it under the OLE, under the 25 kV OLE with a pantograph up. I can operate it with a diesel alternator set. Thirdly, I can operate it on battery power alone. But the 4th mode, of course, is I can combine the power of the diesel and the batteries together to give me a 1300 kilowatt locomotive when there's no overhead power supply. So again, that's around about 1800 horsepower in old money as well. That's 1800 horsepower, which is a very efficiently delivered to the railhead. It's not like it's wrong to compare 1800 horsepower with a class 93 to 1800 horsepower of a class 43 or 37, whatever it is. It's a different concept altogether. So that's some of the generic stuff. Like I say, it's a mixed traffic locomotive. So when we look specifically at passenger operation, what we needed is something to go fast. So it's 110 miles an hour locomotive. Now you probably know that the class 88, which is derived from, is 100 miles an hour. Now we wanted this locomotive to go a little bit faster. It had to be capable of 110. Now, of course, if you gain something with one hand, guess what? You lose something with the other hand. And the way we got the extra 10 miles an hour was to altering the traction motor gearing a little bit. So it is slightly higher geared, is the class 93 than the class 88. So it's faster, but the downside of that, guess what? Is slightly lower tractive effort than a class 88. Certainly in terms of starting tractive effort. We're going to talk about tractive effort a little bit later. It's got rapid acceleration. If you can imagine, 6,250 horsepower locomotive hauling a 5, 6, 7, 8 vehicle passenger train, that is a powerful train. And Network Rail recently did some modelling of a 93 hauling Rachel Mark IVs on the West Coast Main Line, and the report that produced identified that the 93 was much sharper off the mark, much sharper up to 110 miles an hour than a Pendolino. So it just shows you the performance of this locomotive when it can outrun a Pendolino. It doesn't have the top speed of a Pendo, so on a non-stop run it's not going to compete, but certainly on the stopping service on the West Coast, the 93 Mark IV is a better option than the Pendo. So that's something that surprised me. It's got electric train supply, or head-end power as it's often called nowadays, so it's a standard 1000 volt AC electric train supply, so standard kind of electric connections that ETS connections that we've had for donkey's years. And we've got provision for power operated door control, so that's exactly the same kind of arrangement as was fitted to the class 68. So it would be the same modification to the 93 as provided to the 68. Very similar locomotive in a lot of context. That's passenger. In terms of freight, as we said, this locomotive is damn powerful. But of course, we have to be a little bit careful when we talk about the power of a locomotive, especially when we're talking about the power of a 4-axle locomotive, because there's 3 things we need to consider here. Yep, there's raw grunt, raw horsepower, 6,250, that's more than you can shake a stick at. But we also have to consider how that power is delivered to the railhead. So that is tractive effort, of course, the ability of the wheels to push against the railhead. And then the third thing, of course, when you push against the railhead, it's how well those wheels grip the rail, which is adhesion. So we have to consider horsepower, tractive effort, and adhesion. So whilst we've got all the power in the world, we haven't got all the adhesion in the world. So the one thing I would be loath to do is to suggest the 93 is a heavy haul locomotive. Yes, on a nice dry rail, on a nice level gradient, it could pull anything. But when we're talking about pulling trains out the Peak Forest, for example, 3,000 tons of stone out the Peak Forest on a typical Peak Forest day, they have 9 months of winter and 3 months of bad weather up in the Peak Forest. The railhead condition is generally dire. They're built on the side of a mountain. The 93 is not the locomotive to do that. How the hell a class 66 and a 70 pulls the weights of trains out of Peak Forest? I never know. But so again, it goes back to what I said earlier. You can't have a locomotive that does everything. One of the characteristics of the 93 is tractive effort. As we all know, but we're going to see this when I produce a slide a little bit later. Tractive effort when we start away is typically very, very high, but it tails off very quickly with a locomotive. Slightly quicker with some than others, but with a class 93, that high level of starting tractor effort is sustained for quite some time. And that's one of the reasons this is a rapid accelerating locomotive. Again, more about that in a while. One of the things it's got as well, it's got a very heavy duty drawbar strength. So it's we're going to talk about the coupler in a minute. The coupler strength is 90 tons, 850 kilonewtons in new money. And if you think, you know, historically, freight locomotives had a drawbar strength of 56 tons. 90 tons is considered to be about 60% more beef in the coupler. In terms of some of the other things, that's you know, differences with the 93. It's got dual brakes. Well, nothing unusual about a dual brake locomotive. We had them for donkeys years, yeah, but that was air brake and vacuum brake. What we've got in the 93 is an air brake and an EP brake. You know, one of the things that we do, of course, is haul a lot of electric multiple units around with EP brakes. And so instead of having translation kit on board, which converts the pneumatic brake signal into an electrical brake signal, we've actually got a secondary brake system on board, which can operate the brakes on an EMU. And likewise with a coupler, it's a dual coupler. Yeah, we've got, you know, the traditional, you know, draw hook and oops, going ahead of myself here, and draw hook and screw coupler, but I've also got a variable height mechanical coupler. So, you know, this mechanical coupler, like I said, it's a huge 90-ton mechanical coupler. It's a Voith 132. And what the hell's a Voith 132? I hear people saying, well, I don't hear because you're all on mute. But it is the forerunner, well, it's the mechanical part of the new European digital auto coupler. And it's compatible with the likes of the Schaffenberg, the Delta 12, for example. That's fitted to a lot of our EMU stock. So although it's a different manufacturer, it's actually compatible with the couplers that we've got out there now. Environmentally, what a very green locomotive this is as well. What we've got kinetic energy recovery. So I mentioned those batteries earlier, the lithium titanate oxide batteries. Well, those batteries also act as a kinetic energy recovery system under braking. We're going to talk about that in a short while. It's got regenerative braking. So when the driver applies the automatic air brake, the train does less of the braking, the locomotive does more of the braking, you know, converting the traction motors into alternators, and that power goes back into the overhead. And I like that because when I draw current from the overhead, I have to pay Network Rail, but when I put it back, Network Rail pays me. So I like that. And like I said, we can run the locomotive in battery-only operation. I'm not suggesting we're going to run it on the main line in battery operation, but for shunt moves, you know, between stations and depots probably, or within other confined spaces or spaces where or environments where noise is an issue, and you know we know we've got problems with locomotives like the Class 68, for example, with noise. Obviously, we can get around that by using the battery as well. And then finally, in terms of the future proofing of the locomotive, a number of things we've got on board. We've got 5G cellular connectivity, which allows us to stream data to or from the locomotive live. So, for example, you know, the locomotive, as you would expect, it's got full condition monitoring. I can actually monitor everything about the locomotive and how it's performing from a laptop in an office, and you know that's real time through 5G. But whilst we're talking about data, I can also run data backwards and forwards down my train. So if I'm coupled to an intelligent train, which can provide me with data about how the wagons are performing or the coaching stock's performing, if I'm receiving data about, for example, if I have accelerometers on board the vehicle, that can send me data about how the infrastructure is performing. And indeed, you know, I can transmit data about the load as well, so that you know the customer would be interested in that kind of stuff. So full data transmission. Data is big business these days. We're heading towards a digitized rail industry, and so you know, data transmission, data data generally is going to become very commercialized. No surprise, it comes ETCS ready whenever we get the first bit of mainline ETCS operating. I think that's going to be East Coast Mainline in about 3 years' time. I mentioned it's got digital auto coupler, and then finally, the locomotive is modular construction. So, for example, you know, if it's still necessary to remove the diesel engines in 2040 or 2035 in Scotland, they're a bit ahead of the rest of England. You know, we can take the engine out, we can take the cooler group out, we can remove the fuel tank and replace it with batteries or whatever else we need to plug in. Right, before we get into the nitty gritty, any questions from anybody before we press on?
Hi, Carl. Yeah, we've got a couple of questions if you're ready. So,
Yeah.
Julian Heathcote, is there a reason that you didn't go for the AAR 100-ton coupler?
It was Stadler's suggestion that we went for the Voith 132 because I think it's a coupler that they already employ on other traction units in Europe, and so you know it suited the bill, it suited them, and it suited us. So that's the reason why we went for that. So.
Okay, thank you. Next question is from Sam Blacktop. Did you have any particular service in mind when specifying the 110-mile-an-hour top speed?
Couldn't possibly comment. But no, you know, I mean, you know, you don't have to be a rocket scientist to understand what locomotives out there currently hauling passenger services are going to have to be replaced, you know, in the not too distant future. And you know, I think most of you or some of you will have seen the last week before, a couple of weeks ago now, because it's in the public domain. First group have opened an expression of interest for locomotives to replace their Class 68s and Class 57s. So no surprise there. So you know, that might be a service that you might see 93s in the future. We don't know. It's just the first group at the end of the day.
Okay. Another question then from Dean Taplin. At this time, how heavy is the Class 93? And it says presumably it's heavier than the Class 88 with the improved engine and traction batteries.
Oh yes, good question. So yeah, okay. Remember I said earlier, you know, you win something with one hand, but you lose something with the other. So yes, I've got my lithium titanate oxide batteries with one hand. That's a good bit. But I had to lose the rear static brake resistances. A, to free up the space to get the LTO batteries in, but number two, to keep the locomotive below that magical 86 tons. Because if the locomotive goes into the 86 ton category, it no longer becomes an RA7 locomotive, it becomes an RA8 locomotive. So we have to keep the locomotive at 85.9 tons. So I have to sacrifice the rear static brake resistances, but you know what? I wasn't bothered because, you know, we all know that, yes, whilst rear static brakes are useful at conserving brake block wear, I'm not doing anything in terms of energy. You know, I'm not recovering energy with the rear static brake. All I'm doing is burning that energy off through the rear static brake resistances and warming up the atmosphere. You know, that energy isn't going anywhere. You know, I much prefer to use that energy to recharge my LTO batteries, or indeed, if I've got overhead and the pans up, you know, put it back into the wire and Network Rail pays me some money. So yeah, you win some, you lose some, but yeah, fair question.
Okay, thank you. The final question at this stage then from Peter Vincent. You are fitting 5G, but do you envisage 5G towers along the railway?
Oh, well, there's a lot of activity going on behind the scenes, isn't there, about the rail industry providing data infrastructure for the UK. I must admit, whilst I know it's happening in the background, I'm not plugged into it, so I don't know the technical detail, but I do know there's a lot of activity going on behind the scenes with rail infrastructure, 5G infrastructure too. Yeah.
Okay. Do you want to continue then, Carl? And there is one more question come in, but I'll take that later on.
Okay, we'll just crack on for now. So the build program. So 2021 was essentially the design phase of the locomotive. And you've just seen an extra couple of months added to the end of that design phase at the end of 2021. So I encountered 2 months delay. Well, I agreed 2 months delay to the build program with Stadler for two reasons. Well, one reason, but two variation orders. So we altered the design. One of them was the coupler I mentioned earlier. So we did originally specify a Delna 12 coupler, but we did agree to fit this 0.132 coupler on Stadler's suggestion. So that meant a little bit of a redesign of the drag box and everything on the locomotive. It's not, it's not just a matter of, taking one coupler off and sticking a different one on. There's quite a bit to do with the drag box design, etc. But the second variation order was to do with the transformer. Originally, the original specification had the same transformer as a Class 88. So it was a 4 megawatt transformer. But ABB, who provide the transformer, said to Stadler, we now have the next generation transformer. We've got a slightly more powerful transformer than the 4 megawatt. We've got this 4.6 megawatt transformer you can have. And the other advantage of it is it's actually smaller in size. Even though it's more powerful, it's actually smaller. And so what that also enabled us to do, because it freed up a little bit of space, it enabled us to increase the size of the fuel tank. So it increases the range of the locomotive in diesel mode now. So it was quite, that was a win-win situation. And like I say, it gives us that extra bit of power as well. It's interesting actually that under normal circumstances, the maximum power delivered to the wheels is still only 4 megawatts. But one of the modifications to the driver's desk is a go faster button. Give it its proper title, it's got a tractive effort boost button. And what that enables the driver to do is to select this extra power if required. And there's a limit, there's a 30-minute limit to how long the driver can utilize that power for, but 30 minutes is more than enough time for anything. So it's there if it's needed. It's the reason there is a time limit to being able to use this tractive effort boost capability is simply because you're taking the traction motors slightly out of the comfort zone. So although the transformers increased in power, the traction motors are still officially rated as 1 meg, not 1.15. But what Stadler said, the ambient temperature in the UK isn't that clever. It's not exactly tropical. Traction motors are not going to get that hot. Likelihood of a driver using, that amount of power for any length of time is going to be, it's going to be limited, to say the least. But anyhow, we went for it. So like I said, we have encountered a little bit of delay, and that's had a knock-on effect to the rest of the program. As we speak, 93001 is under construction. We are in manufacturing stage, so that's the main bulk of the locomotive, if you like, in terms of the underframe, bogies, and of course the body shell itself. So that's expected to be finished in another 3 months' time. And then we start the assembly phase in July, and that's pretty rapid. Everything is pretty much now. Locomotives are assembled, as we know, in terms of the components. We just plug them in, and that's pretty much it. It's the first in class 93001, and as expected, because it's first in class, there is quite a long type testing program. So that's 4 months worth of testing, and that's all going to be done at Valencia. So there'll be static testing within that phase. Valencia does have a bit of a test track. It's only a linear test track. It's not a very fast test track. Certainly nothing like Velin, certainly nothing like Wildengraf. But it was kind of agreed that this is kind of a Class 88, but with a few dynamic changes. So it shouldn't need to be, it shouldn't need a full approvals process. You're only going to have to really type test and approve those dynamic changes. There's a lot of TSI compliant stuff on board. There's a lot of Class 88 stuff on board. You know, it's just repetition in terms of some components and what they do. I get 93001 February next year, so we're still 11 months away from seeing 93001 shipped to the UK. And then guess what? You know, we've got all the compatibility bits to do, testing, fault-free running, and final approvals, which is about another 3 months worth of work. Is 3 months too long? Don't know. We'll see. And then, you know, we should at the end of the day, you know, get them into service. We'll certainly get 93001 into service next June, and his mates following very rapidly after that at a rate of 2 locomotives per month. So that is the build program. I just want to talk about energy efficiency. You know, I mean, the need to conserve energy is probably more appropriate today than it's ever been. You know, it's almost like every day now we're hearing of energy prices, you know, continuing to rise, and obviously, you know, the recent events in Ukraine are not helping things. So, you know, the need to conserve as much energy as possible is increasing by the moment. And of course, you know, I mentioned a few things on board. You know, we have these lithium titanate oxide batteries, which we can use to supply traction power to the wheels. But of course, I also mentioned the fact that under braking, I can convert kinetic energy into useful energy, into electrical energy, under braking, and ensure that my lithium titanate batteries are, you know, fully charged to the best they're able to be at any moment in time. Obviously, if I've got an overhead, if I've got 25 kV above my head, what happens is the inverter, when it receives power from the motors under braking, it will always make sure the LTO batteries are fully charged first. That's its priority. And there should be, if you're under the wires, because when I take power from the overhead, one of the places that power goes to, guess what, is the LTO battery. So there's no reason really, when I'm under the wires, that the LTO battery shouldn't be anything other than fully charged all the time. But obviously, you know, like I say, I can put power back into the overhead. Nothing new about that. We were doing that back in the 50s. I think the Woodhead route with the Class 76 locomotives, that used to do the same. But another piece of kit we've got on board, and again, this is something fairly common to modern traction units. I've got energy metering. So I've got a device on board which monitors not just what I draw from the overhead, but also it monitors what I put back into the overhead. And like I say, one is netted off against the other, and that's the price I pay for my electricity. What the energy meter allows us to do is very simply pay for what I use. Prior to energy metering, some of you will know we had to pay a standard, what's known as EC for T, electric current for traction, charge to network rail, which was based on basically the type of locomotive, the weight of the train, the number of miles you were doing. So, you know, chances are, you know, as operators, we were paying for more traction current than we really needed, whereas this allows us just to pay for what we use. But what it also drives is a need to conserve energy as much as possible, because, okay, we conserve energy, we also reduce carbon emissions. But if we conserve energy, we save money. And as a businessman, you know, I am very excited about saving money. Now, what this enables us to do, or what this prompts us to do, is to further develop the driver skills. You know, we really need to spend some time with our drivers, you know, not just teaching them to drive economically, but teaching them the reason why, you know. So we have to go back to science. You know, we have to make sure drivers understand, you know, kinetic energy and the potential within kinetic energy, and what we can do with kinetic energy if we have to start braking and all that kind of stuff. And this is why I get quite excited about things like connected driver advisory systems. You know, I think we've all heard of DAS, you know, the original driver advisory system, which didn't go down too well, certainly with the driving fraternity, because DAS basically told the driver a load of stuff you should have already known, whereas CDAS tells the driver a load of stuff he couldn't possibly know, but he would like to know, such as, you know, the fact that Higglebottom Junction, 10 miles up the line, is at a standstill because there's a few trains running late. If you knew that, you would just ease the power controller back and save a load of energy. So there's that kind of stuff as well. So again, a very, very efficient locomotive in that respect. Let's talk about tractor feather very quickly. As I said, you know, horsepower is one thing, but tractor feather is another. And you know, the definition of tractor feather is the horizontal force that the wheel tread exerts on the rail. So it's turning force, if you like, similar to torque, I guess. Now, one of the things we can do in the design phase of a locomotive is to determine the tractive effort characteristics. And I can alter the tractive effort characteristic. In fact, I have done with the Knight 3, I mentioned it earlier. You know, I can adjust the gearing between the traction motor and the wheels. You know, so if I increase the gearing, you know, I'm going to get a faster locomotive. If I lower the gearing, I'm going to get a slower locomotive, but with a higher starting tractive effort. And you know, if you do one, you lose the other, and if you do the other, you lose the first one. So you know, you can't have everything in one package, and that's why historically locomotives have very, very different characteristics, which we're going to look at now. So what you've got a graph there. You've got the vertical axis on the left-hand side, which is the tractive effort force in kilonewtons. So this is the force on the wheels on the rail. And then that bottom axis running on the bottom is speed, you know, because tractive effort does tail off with speed. So let's just have a look at a Class 91 to begin with. Now, a Class 91 is a racehorse. It's very highly geared. So guess what? It's got very low starting tractive effort. But the characteristic of the 91, because it had to get, well, it had to go, 91 is actually 140 miles an hour locomotive, of course, it only goes up to 125. But with a Class 91, you know, that tractive effort needed to be sustained throughout the speed range, otherwise it was never ever going to get up to 140 miles an hour. So this is one of the problems with a high-speed locomotive. You know, you have to sacrifice high starting tractive effort to give you continuous tractive effort right up to maximum speed. So a 91 is a racehorse. The Class 66 is a cart horse. So that's the difference with the 66. So it's got very high starting tractive effort. It's very highly geared. It has to be able to, you know, move away from a standing start, very heavy train on, you know, quite challenging gradients. So very high starting tractive effort. But look at the characteristic of that curve. High to begin with, but at 5 miles an hour, so very low speed, it starts to tail off quite significantly. At 10 miles an hour, it's falling off a cliff. And the tractive effort of a Class 66 falls away very, very rapidly. And you can see there, it's only 30 miles an hour when it falls below that of a Class 91. And this is why a Class 66 is brilliant at pulling a mountain down at very low speed. But it's not a high-speed freight locomotive. It's not an express freight locomotive. It does freight very well at low speed. It's not an intermodal locomotive. They are used on intermodal trains, and you know, they will go up to 75 miles an hour if the gradient is in their favour. But you know, they do not perform very well. I was amazed when I was at GB Railfare. We used to operate 66s, how sluggish they were on intermodal trains. So two varying characteristics. Slap bang in the middle, and here's an example of a mixed traffic locomotive. This is the Class 68 diesel locomotive. So because it's mixed traffic, you know, it's trying to be a bit of both. And guess what? The starting tractive effort is somewhere in the middle. But it actually does pretty well because it maintains pretty much the same tractive effort as a Class 66 from about 15, 18 miles an hour, something like that. And obviously maintains that up to 100 miles an hour. So you know, quite a good performing locomotive, the Class 68, not to be underrated. Now, the 93, obviously in hybrid mode, so this is when we've got the diesel and the alternate diesel and the batteries working together. like I say, it's only around about 1800 horsepower, 1750 horsepower, whatever it is. So yeah, reasonably good starting tractor's effort, but it tails off very quickly from about 10 miles an hour. And it's that mid sort of starting tractor's effort speed, 20-25 miles an hour, where it drops away from a 68. But you know, when you look at that graph, when you get up to about 85, 90, it's actually not that far behind a 68. And if it wasn't for the fact I wanted that extra 10 miles an hour, the gap between those two lines would be a little bit closer as well. Okay, the 93 really comes into its own when we put the pan up. And so masses of starting tractor's effort. But the characteristic there, of course, look how long that straight line, that starting tractor's effort continues for. It's beyond 30 miles an hour. And I've still got maximum starting tractor's effort. Very different characteristic to any other traction unit on that graph there. And of course, you know, when the driver selects that tractor's effort boost, that tractor's effort is sustained, starting tractor's effort is sustained quite a bit further, up to about 35 miles an hour before it starts tailing off, and it maintains a very high level of tractor's effort all the way up to 110 miles an hour, more than a Class 91. So there's the characteristics of Class 93s in terms of tractor's effort. Any questions before we go any further?
Right, we've got 3 new questions then, I think. No, we've got more than that. Right, firstly, are all the locos being built in Valencia or only the first in class?
No, they're all built in Valencia, every single one of them. Yeah, that's Stadler's locomotive manufacturing plant. Yeah.
Okay, and next question then, without the rheostatic resistance, what happens to the electricity generated under braking once the battery is full and the loco is away from the OLE?
Yeah, back to friction braking, I'm afraid.
Okay, so back to your brake pads then. Yeah.
Yeah.
What's the range of the loco off the wires?
Yeah, it all depends on, you know, how it's being driven. It all depends on the gradient profile. It depends on the weight of the train. But on a light passenger train, it's about 1,200 miles, so it's quite significant.
Yeah. Then final question in this stage then, given the experience with wheel slip on Class 68s, will the Class 93 have any addition enhancements such as creep?
Oh, yeah, no, yeah. Good question. So the Class 93 has a similar traction control system to the Class 88. The traction control systems are so different on modern locomotives to what they were when the 66s were built, and indeed the 91s for that matter, which use thyristors still part of the traction control system. Of course, new locomotives use IGBTs, which are a much faster firing or switchable transistor. So you get the advantage of having greater controllability, but it's also intelligent as well. So yes, creep is critical. You always want that lead axle to creep, and the reason being, of course, it conditions the railhead. So axles 2, 3, and 4 can do a bit more in terms of gripping. But yeah, we talk an old-fashioned term, SEPEX. Of course, these have got a more modern equivalent of SEPEX. So each motor can be controlled individually, but switched very quickly as well. And there was one story, and I think there's somebody in our engineering community who's got a video of a Class 68 on Velin, on the test track at Velin, hauling a 2,500 ton freight train on a wet rail, and one of the wheel sets was slipping like hell, but the 68 got away with this train no problem. But the interesting bit is the reason that one axle was slipping, it was the only axle that was powered at the time. It switched out the other 3 axles. So the 68 had the ability to pull that train away on one motor. So that just demonstrates how damn good these systems are. I'm under no illusion that on a dreadful railhead on a quite a challenging gradient, you're going to have problems. it's a 4-axle locomotive at the end of the day. So, you know, I know what wheel slip is like, and I know how damaging it can be, irrespective of how intelligent or how refined the traction control system is. So again, you know, that is really, you know, one of the factors in determining how I deploy the locomotive. Yeah.
Okay, another question then on tractive effort. How does a class 88 compare on tractive effort versus speed?
Yeah, so if you look at that blue line, the 68, the 88 is exactly the same. I think it's 310 kilonewtons for both a 68 and an 88. So they both have exactly the same starting tractive effort because they've got exactly the same traction control system. They've got exactly the same traction motors. They're both 1 megawatt motors, same as the other on 93. The difference with an 88 is that starting tractive effort is sustained longer than it is with a 68.
Okay. And then a follow-up question on the range. Obviously, you told us about the range with a passenger train. What's the maximum range on a freight train with, say, 2,400 tons of train?
Oh, yeah, you know, I think one of the ways to look at this is, you know, we've done quite a bit of modelling on how we perform with these locomotives, and I've actually determined a kind of a limit to how I want to push this thing to begin with. So whilst, you know, on a dry rail, on a less challenging graded route, yeah, we could haul 2,500 trains, no problem. You know, I would want to demonstrate and prove that concept first. So, for example, I wouldn't go straight into operating, you know, heavy aggregates trains, or even lighter, much lighter intermodal trains on routes where I'm off the wires for a long time. So it's too early to say at the moment, but you know, I'm just being a little bit conservative with how what I apply this locomotive to.
Okay. And the final question then at this stage, thanks for the talk, by the way, that's from George. He says, did you take your spec to several suppliers or did you just go to Stadler?
Yeah, good question. No, just Stadler, because, you know, they were the only locomotive manufacturer which had a UK locomotive platform. You know, they had the 68, the 88. So it just made perfect sense. If I wanted a locomotive pretty quickly, I have to go for an existing UK design.
Okay, all right. Thanks then, Carl. That's it for questions at this stage.
Yeah, okay. I think actually we're just about finished. So going back to the application of the locomotive, you know, there's a few examples of the ideal kind of operation for the Class 93. So starting with that intermodal service and working clockwise, the 93 is a cracking intermodal locomotive. Intermodal trains are not that heavy. You know, typically they're between 1,250, 1,500 tons. Yeah, you get a few that creep above that, but typically they're not that heavy. And the reason they can't be that heavy is because, of course, even with a 40-foot container, I can't load the container to more than 31 tons because that's the limit on a UK articulated lorry trailer, of course. So that's why, you know, intermodal trains, and I mean, they look heavy, don't they? When you look down the side of a 36, 38, 40 platform intermodal train, you think they're as heavy as hell, but they're not. It's not like hauling 2,500 tons of aggregate. So a perfect locomotive for intermodal operation. Interestingly, that DRS train there, that's for Sierra 45, I think it is. It's the Daventry to Moss End intermodal service. DRS were telling me, you know, when they had a 66 on that train, a 66 would wheeze across the top of Shap at about 10, 12 miles an hour with a 1,400 ton train behind it. That Class 88 is doing 55 miles an hour at the top of Shap with that train. So it just shows you the difference in performance between a diesel engine and an electric locomotive. And of course, what that enables you to do is significantly reduce your sectional running times, which significantly then reduce end-to-end journey times. We did some modelling I think one in particular was something like a Felixstowe to Moss End service via the GE in the North London line up the west coast. And with a 93 on the front, it got to Moss End 3 hours quicker than what it would have done with a 66 on the front. And that's at 75 miles an hour. So it just shows you the performance gains that the power generates, and that's through delivering better acceleration and more importantly, performance on rising gradients. The next one round is one of our 47 Horlinger Flirt unit. So this is rescue and recovery. The 93 is the perfect rescue and recovery locomotive because it's got all kinds of brake systems and coupler systems. And as you probably know, we can't agree in this country, never mind what coupler to use, but we can't agree what height for couplers. I mean, the Delna 12s, for example, in this country, we've got 5 different heights for a Delna 12 in the UK. Can you believe that? What happened to standardization? Anyway, there we go. Next one down, testing. You know, the 93, because of its 5G cellular connectivity, you know, I can put fully instrumented pans on the 93 and transmit the data from that pan straight back to a control room somewhere full of people with monitors. I don't need a load of test vehicles behind it, people sitting at monitors. I can just stream that data, you know, back to an office somewhere. That bottom right there, that's a lot of the stuff that we do, you know, rolling stock services. Okay, you know, that's a what is that? Is that 321 unit? I think it is, isn't it? So yeah, all kinds of rolling stock services we can point the 93 at. Next one round, yes, 68's a bit of a troublesome child, but a bit noisy. Neighbours don't like them, so you know, that would be an ideal opportunity potentially for a 93. And then finally, you know, that's one of our 47s on a passenger train. Open access operation, any other type of passenger services, whether it's, you know, charter or whatever. So, you know, we can point the 93 at all these kinds of markets. But, you know, what is interesting, going back to this one size fits all locomotive, you know, we've had this in this country for a while, you know, because, you know, 66 has been, you know, the be all and end all of all freight operations. Not like that on the continent, of course. But I just very quickly, I wanted to talk about intermodal operation. And I just want to show this video a second.
Containerization is a mighty big word, but what it means is that goods are packed into containers all the same size, which can be handled by the same cranes and the same lorries and loaded onto long trains of the same size trucks. Freightliners only started in 1965, but by next year they hope to have 80 Freightliner routes carrying 1 million containers a year. 5 nights a week, around midnight, a Freightliner train leaves Harwich for Manchester. It travels at 75 miles an hour and gets in by breakfast time, and there are no stops on the way.
Yeah, I love that video because, you know, it just demonstrates how stagnant we've been in the rail industry. You know, we think we're pioneers. We think we're, you know, we're still leaders in you know, delivering modern, you know, train operations, one thing or another. But we were operating 75 mile an hour intermodal trains in 1965. That was 57 years ago. We're still running at 75 miles an hour to this day. So we haven't moved one iota in 57 years. And, you know, to put that into context, it was only 66 years from Orville Wright flying his first powered aircraft to putting a man on the moon. And in 57 years, we haven't moved on one little bit. And one could argue, actually, we've gone backwards because the average speed of an intermodal train is a pretty sight slower now than it's ever been. You heard the commentary there, and there are no stops along the way. You know, I was operating intermodal trains in 1980. You never went onto the slow line once upon a time with an intermodal train, never mind into a goods loop. So, you know, one of the things that we need to do is really look at speeding up intermodal trains and getting some, playing catch up, I guess, with a little bit with passenger train advancement, you know, the speed of passenger trains. And I guess the other thing, I don't know if anybody recognised or took note of the 4-character head code on the front of that locomotive. Intermodal trains back in the 60s and 70s used to run as a class 3, not a class 4. So again, that's another retrograde step, but there we go. Just to end up, you know, there are critics that say, you know, you shouldn't have 4-axle locomotives on intermodal trains. It should be a 6-axle locomotive. Well, just look at the continent. Every single country in Europe is using 4-axle locomotives on intermodal trains because they're not that heavy. These are a mixture of Siemens Vectrons and Bombardier Trax locomotives, but they're all 4-axle locomotives. So that's it. That's where we are. So that's taken us to the end of the presentation. So any more questions from anyone?
Brilliant. Thanks a lot for that, Carl. We've had a couple more questions come in then. Hi, Carl. Very interesting presentation. Great to see how far you've evolved since our class 357 and 375 unit moves, which seems an age ago. Keep up the excellent work. And that's from Glyn Swift, who obviously knows you.
Hi, Glenn.
The next question is, are the batteries always charged while underway, or is it envisaged that it may be required when in the depot?
Yeah, so the 3 ways of charging the batteries. So anytime the pantograph's up, the batteries will charge. Anytime the diesel alternator is running, the batteries will charge. And of course, under braking, as we saw earlier. So 3 different modes of charging the batteries.
Okay, thank you. That's it, I think, for questions. So thanks a lot, Carl. It's an excellent presentation. If Jason Groombridge is still on the line, I'd like to ask Jason to propose the vote of thanks, please. If you're there, Jason.
Yeah, sorry, Martin. Yeah, I'm here. Apologies.
Beginning to panic.
Good evening, everybody. Good evening. No, well, yeah, I'd just like to do the vote of thanks then. So, Carl, first of all, thank you to you for a really interesting presentation, actually. And as you know from our interactions, this sort of technology is something that Porterbrook that I work for, we're close to our heart. So it's good to see others in the industry taking some of these technology areas forward. I mean, you started your talk talking about the 5 areas you're going to cover, which you did very well, how the whole concept started out, quite a lot of update on the technical specification, the build program, some discussion around the performance and the capability and the markets you're doing, you're looking to put the locomotive into. Lots of interesting technical information around the specification. And the assessments that your business has gone through to choose this particular locomotive as being the best. And I found that the bit around the battery technology was quite interesting, actually, again from some personal experience recently. The technology is moving quite fast, so to be able to pick the right technology in the right way is really good. And it sounds like you've got a product that's got a really good balance for different performance parameters that meets what you need for your business, and that's good. I also noted, noting the point around being able to deliver all of that capability, speed, power, the different technologies, traction technologies, and have all that under the 86-ton limit to stay within your RA7 rating. So that's good. And the recovery, the regenerative braking and the kinetic energy recovery through the batteries, again, interesting technology points. There's still some work to go, but wish you well for the rest of the program and successful service entry in June 23. And I think as a centre, we probably look forward to you coming back in a couple of years' time and giving us an update on how it all went and the lessons that you learned. But
hoping to be retired in a couple of years' time, Jason.
What's that? Sorry.
I said I'm hoping to be retired in a couple of years' time. Maybe 18 months.
Yeah, but thank you very much. The range and type of questions obviously shows there was a lot of interest in the audience. So thank you very much. And I'll just ask everybody to thank Carl in the usual manner, if that's okay.
Yeah, no, thanks very much, Jason. Much appreciated. So anytime you want me to come back, give an update, just let me know. No worries at all.
That was brilliant. Thanks a lot, Carl. Thanks for the presentation. Thanks for the questions. Just remains then to hope that everybody has a good evening. I think Carl said he was going to the Brunswick. Sadly, I can't be there. I'm a few miles away from there, but hopefully Carl has a good evening in the Brunswick. The next lecture that we've got is on Wednesday, the 13th of April, and it's from Loram UK. And the paper is entitled Collected, Operated, Maintained and Delivered. So that's Wednesday the 13th of April. And again, it's via Zoom starting at 6 o'clock. So the Zoom details are on the IMechE website. So thanks a lot, everybody, and enjoy the rest of your evening.
Yeah, thanks again, Martin, much appreciated. Bye, everyone.
Yeah, thanks a lot.